Hey everyone, so welcome to the lecture, continuing on with our angular momentum operators. So last time we saw that that the only things that commute in the set of components of the angular momentum vector were the total angular momentum, L squared, and any of the the components, like for instance L squared and LZ, or L squared and LX, or L squared and LY. Those all commute, which means you can pick one set like this and find simultaneous eigenfunctions and eigenvalues of those two operators. Okay, so that's cool. But it does mean that if you know LZ, right, you don't know much about LX or LY because those do not commute. Okay, but you can know about the total. All right. Okay, so we're going to look for, my pen is being a little crazy. Let's see if it settles down. Look for simultaneous. Okay, hold on a sec. I'm going to stop this for a minute. I'll be right back. Okay, I'm just going to test really quick if this is only when I'm recording. We'll see. Okay, we're going to look for simultaneous eigenfunctions and eigenvalues of these guys. Yeah, the pen is being bad. I'm very sorry. I hope it'll calm down. Okay. All right. So to do that, right, we need to sit down and think about, of course, what do these eigenvalue and eigenvector equations look like? And we're going to start with, we're also having a lot of lightning and thunder right now. Okay. Blame the thunder for my pen. Okay, so we're gonna look for simultaneous eigenfunctions, and we're gonna so this means that we're gonna have L squared f is equal to, you know, some eigenvalue times that f, and these are the eigenfunctions f, and Lz acting on f is equal to mu f. Okay, so in other words, it's the same functions or set of functions, right? F that satisfy two eigenvalue equations, or eigenvector eigenvalue equations, one with the L squared operator and one with the LZ operator. And this is these are their eigenvalues, lambda and mu. We have no idea what they are yet. We don't have any idea what the F's are yet either. So that's where we have to start. And we're going to start by defining ladder operators very similar in spirit to the ones we used for the quantum harmonic oscillator. Okay, so let's take a look at those. I'm going to start with ladder operators. So ladder operators. Okay. And they look like this. L plus minus is equal to Lx plus minus I Ly. Okay. All right. There's two of them, obviously, an L plus and L minus. They're both operators, and of course, they're in terms of these other operators, Lx and Ly. All right, and let's take a look at the commutator between Lz and the ladder operators. Okay, all right. So let's look at the commutator. So we're going to have L plus minus. Sorry, Lz first. L plus minus commutator. Okay, so let's write it out. So we have Lz and then L plus minus minus L plus minus Lz. And we have here that this is, let's write out our L plus minus. So Lz times Lx. And I'm going to leave the hats off because there's just too much to keep track of. Plus minus I Ly, and then minus our Lx plus minus I Ly times Lz. All right, Now, you can see we'll probably be able to write these in terms of other commutators. So that's what we're going to do. Okay, so let's just sort of multiply through where we can. So we're going to have LZ times LX, and then plus minus I LZ times LY, and then minus LX LZ, and then minus plus, right? Notice we're doing that because we have a minus sign here. LY LZ. All right, so let's write it out. What do we got? Notice we have an LZ LX minus LX LZ. So that's the commutator of LZ with LX, and we know exactly what that is. Okay, and then we have another one, LZ LY, and a minus LY LZ, right? See the minus sign switched from this, got it? So we're gonna go plus minus I times the commutator of LZ LY. Okay. All right, fine. So if we write out what these are, right? So the commutator of LZ LX is IH bar LY. Okay. The commutator of LZ LY is minus IH bar LZ. You can go look those up if you don't remember. Okay. So we have IH bar LY, and then plus minus, I hope the power doesn't go up. It might. I times the commutator minus, which is minus I H bar LZ. Wait a second, why do I have LZ on here? No, that's not right. LX. Yeah, LX. Let me double check that while I'm I'm waiting for the power to go out. Let's see. Let me double check all my commutators here. Okay, take a little break. Oh, shoot, that's the wrong lecture. Okay, so we have LZLX. It's IH bar LY, got that right. The ZLY is minus IH bar LX. Good, all right. Okay, so that's good. All right, so now we're gonna deal with this minus sign. And so we're gonna have IH bar and then LY and then minus plus LH. Oops, why don't I have this I here? Oh, I screwed this up. Let's start over. Okay, we're back to this point. Okay, I times I minus 1 with the other minus just gives you positive 1. So this is not going to change this sign at all. So I'm going to put that out in the front. I'm going to have H bar LX plus minus LX, and then plus IH bar LY. Okay, we're back to my place in my notes where we were. Okay, and you can see what this is, right? This is, let's see, so if we go back up to our ladder operators here, let's look. So we have L, and I think I'm missing a plus minus somewhere. I do feel like I'm missing one. No. Let's see if I can figure out what went wrong here. Not sure. All right, so what I have in my notes, we'll have to see if this is right. Plus minus H bar L plus minus. So let's see. Let's say it was LZ L plus, right? That would be, so we get the top sign. So we'd get H bar L plus, right? which is Lx plus ILY. And what would we get here? Yep, plus ILY. Okay. What about if it was L minus? We would get H bar L minus, and this would be minus H bar Lx. And then plus H bar Ly. Okay. Yeah, so it does work. Okay, so this is the answer to this commutator. All right, and I'm not going to prove this, but you can do that yourself. L squared with L plus minus is in fact 0. So these two things do commute. Okay, so the LZ does not commute with L plus minus, but the L squared does. All right, so if F is an eigenvalue of L squared and LZ, okay, then, so now we can't have 3, right? It's not, it's, and the L plus minus is not compatible with LZ, right? It's compatible with L squared, but not LZ. But so you can't have like a simultaneous eigenfunction of all 3. But you can say, hey, if we have our F function here, if it is an eigenfunction of L squared and LZ, right, then also L plus minus acting on F must be 1, right? So this must also be an eigenfunction of L squared and LZ. Okay. All right. So we're going to use that that knowledge in our next slide. So I'm going to get a new slide here, and I'm going to name it just so we can keep track. Okay. All right. So let's keep going. All right, so what do we have? We have we want to say that this L plus minus acting on F is an eigenfunction of L squared and LZ. All right, so let's act LZ on it and see what happens. Okay, so I'll get another color here. So we're going to act LZ. LZ acting on our L plus minus on F, right? So this should be an eigenfunction, this whole thing together. All right, so let's write it out. Remember that the L plus minus is Lx plus minus ILY, okay? So we have, I'm gonna sort of bring this in, but I'm gonna write it out first. So we have LZ, then we have Lx plus minus ILY. Actually, before I do that, sorry. Okay. Before I do that, I want to write it as a commutator. My pen, please, pen, stop. Okay. All right, so let's just notice that if we have LZ commutate with L plus minus, okay, that is LZ L plus minus minus L plus minus LZ, okay? And if we look over here, we have an LZ L plus minus. This is very similar to what we did before when we were doing a bunch of machinations with our commutators. So look, we have one term here that's going to be LZ L plus minus. That's right here, right? So you notice that this thing, if we added a term that looked like this, right, then we could write this as we could write the commutator in this expression. So in other words, I'm going to write LZ L plus minus. And we're missing this term, right? This term doesn't exist here. All we have is these two guys, which is right here, right? Acting on F, obviously. There's an F here. So now we just need to add in this term. Okay, so plus L plus minus LZ acting on F. Okay. All right. So now we know the commutator. We just derived this exact commutator, right? So let's remind ourselves that LZ commutated with L plus minus was plus minus H bar L plus minus, right? Okay. So we can write that out. So we have, this is going to be L plus minus, plus minus H bar L plus minus acting on F. Okay. And now this guy here, we ought to write down our other equations that we didn't write down. Let's write them down in our little purple color over here. We didn't write them all down. Let's go back because I didn't bring them over. But they were the eigenvalue, eigenvector equations. Okay, so we have the LZ acting on F is equal to mu F, and L squared F acting on L squared acting on F is lambda F. Again, we don't know what lambda or mu are, right? This is what we're trying to get to. We don't know what F is either. Okay, but here I have something acting on the F. And then this guy here, LZF, as we can look over here, is mu F. I'm going to go back to my sort of orangey color. So we have plus L plus minus mu F. Now notice that mu F is just mu is just some number, right? It's an eigenvalue. So I can move that through and just have L plus F here. So in other words, here we go. So we have plus minus H bar. We have L plus minus F. We have plus mu L plus minus F. And now I'm going to group all my numbers. I have mu plus minus H bar on L plus minus F. Okay? And I'll be right back. Just going to check something real quick. See how something's doing. Hold on. Pardon the interruption. Okay. All right. So what we see here is that the, and I'll put a little brackets around this guy here. You can see that the, when the L plus minus operator acted on F, it raised the eigenvalue by a factor of H bar. Remember when we did the harmonic oscillator way back when in 302, how we had the raising and lowering operators, those ladder operators, how they raised the energy by a factor of H bar omega when you applied them to psi. It's very similar. When we apply the L plus minus operators, they either raise or lower the eigenvalue of LZ, right, by H bar. Okay. All right, so we've got that. Let's see where we can take this, or where this is going to take us. But this is very useful information, as we'll see, just like it was when we did the harmonic oscillator. Okay. So again, let's just write it down. I'm going to write it down in a different color here. I'm going to go for our pink. We got a nice kind of light pink here. So I'm going to write it down. L plus raises the eigenvalue of LZ by H bar. L minus lowers the eigenvalue of LZ by H bar. Okay, raising and lowering operators again. And remember that the eigenvalue mu is really the value of LZ, right? It's kind of like when you act the Hamiltonian operator on psi, you get back the energy of the particle, right? By acting the Hamiltonian, which is the total energy operator, on psi, you return the value, right? The energy of the particle. Similarly, here, when you act Lz on your whatever the eigenfunction is, you get back the value of Lz. What is Lz, right? So what is the z component of the angular momentum? All right. So we're keeping that in mind. You can't keep raising forever, right? Because if you keep raising the value of Lz, like how big Lz is, so imagine you have an angular momentum vector, it's pointing off into space, it's got a particular z component, right? It also has x and y components, but it has z component, it has a length, L squared. If you keep raising the value of Lz, you're going to, at some point, raise it past the total length of the vector. You can't do that, right? So there's going to be some kind of top rung past which if you raise, you're going to have 0, right? You're not going to have any more length. So basically, there's this top rung, and we're going to call that, so top rung ft, that's for top, okay? So some function such that if I try to raise it, so that's L plus, and this is a t, okay? You get 0, okay? Can't be raised anymore, right? Not going to get any more out of it because you can't go past the total length of the vector. All right. So let's let h bar times L be the eigenvalue of Lz at that top rung. Right? That means that Lz on the top rung function, eigenfunction, is going to be h bar L. We're just writing it that way. I could have written, mu t or something, but just writing it this way is it's going to be convenient. Okay. Ft. And of course, L squared also, Ft is also an eigenfunction of L squared because every eigenfunction of Lz is also an eigenfunction of L squared. So we have L squared acting on Ft is equal to some lambda that we don't know, Ft, right? Okay. All right. So we'd like to calculate this, right? So we'd like to know what this lambda is. All right, so to do that, I'm going to write L squared in terms of my raising and lowering operators, okay? All right, so remember, L plus, we haven't done this yet, but if we write L plus L minus times L minus L plus, probably going to get some squared terms in there and maybe be able to identify an L squared, okay? So let's see, what is that? It's Lx plus minus ILY. And I feel like I want to do that in a different color, so just hold on a second. I want to erase that. Just so, because this is kind of an aside because we've got to derive, I'm sorry about the pen. It's really bad. Okay. We've got to derive the, we've got to derive the, what L squared is in terms of L plus L minus, so it's kind of an aside. So L plus L minus times L minus L plus, that's going to be Lx plus minus ILY. And then remember, we're going to switch around the sign. So this is going to be Lx minus plus ILY, right? Because if this one's the top sign, this one has to be the top sign. So if this one's plus, this one's got to be minus. And this one's minus, it's got to be plus, okay? All right, so now let's multiply through. So we have Lx squared, Lx times Lx, which is Lx squared. Okay, and then, so that's these two. And then this one here. And then it's going to be minus plus I Lx Ly. And then this one here is going to be plus minus I Ly Lx. You can probably see where that's going. And then this last two here is going to be, so we have I squared, it's going to be minus 1. And so let's just think it through a little bit. So we're going to have a minus 1 on the square, right? So I'm going to write them down like this. Plus, minus, minus, plus, times minus plus, times minus ly squared. And we got to figure out all the signs here. So let's think it through. So if this is a minus sign, that's going to change this to minus plus, right? So, and then you're going to have minus times minus is plus, and plus times plus is plus. So this is going to be plus. Okay, let's write it down. Lx squared, and I'm going to bring the ly squared over here, plus ly squared. And then here, we have a commutator. So let's figure out what commutator is it. Well, we have a plus, a minus Lx Ly, right? So this is going to be minus plus I Lx commutated with Ly, okay? So notice the signs here, right? It's got to change. So it's got a minus sign out front, and we took care of this inside because this is going to be Lx Ly minus Ly Lx, and so the sign should work out. Okay, so remember what this is. This is I h bar Lz. So we're going to write it all again. So we have Lx squared plus Ly squared, and then minus plus I, and then I h bar Lz. Okay, so those two i's are going to give me a minus 1. It's going to change this to plus minus. So we're going to be Lx squared plus Ly squared plus minus h bar Lz. Okay, all right, fine. Now the cool thing here is that I can make this in terms of, I can write this in terms of L squared, because remember, L squared is Lx squared plus Ly squared plus Lz squared. So these two things are L squared minus Lz squared. So we write this one more time, is L squared minus Lz squared plus minus h bar Lz. Okay, fine. Okay, so if we wanted to write our L squared in terms of the raising and lowering operators, right, it would be this. We would have L squared is equal to L plus minus L minus plus, and then plus Lz squared, because that's going on the other side of the equation, right, from this here. And then minus plus, and I think, yeah, I feel like I have a sign, is it minus plus now? No, plus minus. Plus minus, no, minus plus. I knew it was minus plus. Minus plus. Okay, it's got to change sign from here. It's plus minus here. It's got to be minus plus when I bring it to the other side of the equation. So minus plus, and then h bar Lz. Okay, now this is going to help us. Okay, it's going to help us find what happens when you act L squared on the top function here. Okay, so let's do it. I'm going to go back to my sort of pinkish purpley thing. So now we're going to act our L squared using this. So L squared acting on the top ft is equal to L plus minus, L minus plus, plus, and actually I'm going to choose which one I want of these. So I'm not going to use the generic thing that has both of them, right? Okay. I'm going to choose which one, because what I want is I want the one that'll make it so that when I act on ft, I'll get 0. That'll get rid of this term for me. So I want that, the bottom sign, L minus L plus, and then plus LZ squared. And then I'm taking the bottom sign, so plus H bar LZ acting on our F top. Okay, let me check the signs and everything. Yep, looks good. So let's go through the motions here. L minus, L plus on F top. Okay, and we know that this guy acting on F top just gives us 0. That whole term's gonna go away. That's awesome. Then plus LZ squared acting on F top, and then plus H bar LZ acting on F top. Okay, but we know what these do, right? This guy here is H bar L F top. This guy here is two values of two applications of LZ. Okay, so we have LZFT, that's going to give us H bar L FT, then apply again, then you're going to get H bar squared L squared, right? Okay, so I hope you can, I'll just do it real quick here. So we have LZ acting on LZ FT, that's LZ acting on H bar L FT, then the LZ acts on the FT again, and we get H bar squared L squared FT. Okay, all right. So here we're left with H bar squared L squared FT plus H bar L FT. And that gives us H bar squared L squared plus H bar L FT. Okay, so we've just seen what the eigenvalue is. I'm going to write it slightly differently. I'm going to write it as H bar squared. Let me see if I can write it as H bar squared. Where do I have too many? Oh yeah, I forgot a factor of H bar right here. Sorry about that. I hope you guys caught that and we're like, what's she doing? There we go. Okay, so we're going to have H bar squared L, oops, L. Let me erase that. Sorry about that. So we're going to have L and then L plus 1. And so that's a little different, the formula, but this comes out to the same thing. And this now is lambda, right? So this is what happens at the very top for the very top function. Okay? All right. Okay. All right. So now we know something, right? We know the form. If this is the value of LZ's eigenvalue, then this is the value of the total angular momentum. Okay. All right, so let's now think about what happens when you start lowering, right? There's got to be some bottom rung, right? After which you're lowering it to 0, right? Again, where you get 0 because you sort of run out of room. Okay, so we're going to look at that too and try to tie these two things together. All right, let's get another layer. And again, I'm going to label it. Okay, great. All right, so what do we have? Let's just write it down here. We had our LZ on the top function is H bar L F top. And we figured out that L squared on the top function was H bar squared L plus 1. Okay. We still don't know a whole lot about what's going on, but we know something. Okay. Now let's do the bottom function. So we know that we can't keep lowering forever. So L minus on the bottom, FB is got to be 0. And let's let LZ acting on FB be H bar L bar. So some other L, okay, on FB. Okay. And Again, we're going to let L squared on FB be some lambda that we don't know on FB or times FB, right? So we need this lambda. So we're going to do our same old thing we did before. I'm going to write L squared on, and I'm going to act it on F bottom. And I'm going to choose the other version of L squared with the minus being first. So when it acts on FB, it'll give me 0, get rid of that term. So I have L plus L minus plus LZ squared minus, so now we have a minus H bar LZ acting on our FB. Again, when this acts on the FB, it gives me 0. This term's going to go away, so I'm just not even going to write it. So I'm going to write LZ squared FB minus H bar LZ on FB. And, oops, I don't need those parentheses, but, oh, here we go, I'll do that. Okay, so this one's just going to give me H bar L bar, or H bar squared L bar because of this. This is going to give me the same similar thing, H bar squared L bar squared. Okay, a lot of bars in there. So this one's going to be H bar squared L bar squared times FB. And this one's going to be minus H bar squared L bar times FB. Okay, which gives us all together H bar squared L bar squared. Sorry, I wanted to write that in the other form that we wrote before. So, sorry about that. I did not even think. And H bar squared L bar plus 1. Ooh, no. Big mistake. L bar minus 1, not L bar plus 1. Okay, it would be bad if it was L bar plus 1. Okay, so it would have been the same as the other one that we had. Okay, great. All right, so now, but you know, like I said, like we had before, up here, this was L plus 1, right? And this one is L bar minus 1. These two things really have to be the same, right? It's not like they're somehow this is that you would have different eigenvalues. Well, different that you would have different form of eigenvalues. Okay, and this is going to tell us something about what L can be. All right, so let's write down the equivalents that we need. So we need L H bar squared L plus 1 to be equal to H bar squared L bar minus 1. Okay. Okay. When is that possible? Well, you could have L bar equal L plus 1. Does that work? Okay. Well, let's see. So if L bar is L plus 1, let's look at this term here. So I have H bar squared, right? We have L plus 1. Then we have L plus 1 minus 1. And indeed, this becomes H bar squared L plus 1. Okay, that works. But this would mean that the bottom rung is 1 unit higher than the top rung, right? Because that's if you say L bar is L plus 1, then the bottom rung is 1 higher than the top rung, right? Because the top rung is the L bar. Okay. No, sorry, the bottom rung is the L bar. The top rung is the L. Okay, so this thing doesn't make sense because remember this is the top rung from F top, right? And this guy is from F bottom. So the eigenvalue for the bottom function can't be 1 greater than the top. That doesn't make sense. So that solution doesn't work. Let's try, so this is a no-go. Let's try L bar equals minus L. Okay, does that work? Well, let's see. H bar squared. Then we have the L bar, so that would be minus L. And then we have minus L minus 1. And this would be pulling all the minus signs out. H bar squared L plus 1. That does work. Okay, so that's great. Now this is more meaningful because look what's happening. right? The bottom rung is minus L and the top rung is plus L, okay? I hope this reminds you of something, right? If we have L equal 1, right, in our spherical harmonics, right, they can go from minus L to L in units of 1. So minus L, minus 1, 0, 1. Or if it's, or for L is 2, minus 2, minus 1, 0, 1, 2, right? So I hope this makes some sense. So the bottom rung is minus L. The top rung is L, okay? All right. So that makes a little bit more sense. So the eigenvalues, it's right there in blue. Eigenvalues of Lz, so the z component of angular momentum, go from L, minus L to L in integer steps. Because remember our raising and lowering operator was going to raising and lowering them by plus or minus, raising by h bar, lowering by h bar, right? And notice that the eigenvalues are h bar L, right? So it's going up and down by integers, right? Integer steps, not steps, integers, not steps. Okay. All right. Okay. So, well, let's write it down again. So we're going to look at our functions. So in the book, and I'm not going to prove this, it's just a little bit long, a little bit pressed for time. So I'm thinking maybe I'm not going to prove this. Go look in your book. But maybe you might have guessed already that the eigenfunctions, so if we look at them, we've got the eigenvalues. But the eigenfunctions, right, are the spherical harmonics that we saw before. Okay, hopefully that's not too surprising. So the F's are the YLMs that we got before from solving the Schrodinger equation and the angular part of the Schrodinger equation. Okay, so YLMs of theta and phi. So in other words, LZ acting on YLM is equal to H bar L YLM, and L squared acting on YLM is equal to H bar squared L plus 1 YLM. Okay, and in fact, this isn't quite what we want, right? We want this is actually M, right? Because remember, the M's can go from minus L to L, okay? So let's go back here. So it was the M's that I was talking about before. I should have said M. I don't know if I did. H bar M, that can go from minus L to L. So you pick L, M goes from minus 1, minus 2. Well, sorry, pick L to be 2, let's say. Then M is minus 2, minus 1, 0, 1, 2. I think I said L before, but I really meant M. Okay, so so these are the actual eigenvalue and eigenvector equations solved by the spherical harmonics with the correct eigenfunctions. And when we solved the TISE in 3D, we inadvertently solved for simultaneous eigenfunctions of the Hamiltonian, right? L squared and LZ. Just inadvertently did that. Okay. So if we come down here, we'll do a summary. So we have simultaneous eigenfunctions. Of Hamiltonian, L squared, and LZ. Okay. So when we actually solve the TISE, so in other words, we have, you know, H hat acting on psi is equal to E psi, and L squared acting on psi. Remember, psi has a radial component that's in there, but that's not going to be affected by L squared and LZ. Okay. Is h bar squared L plus 1 psi, and LZ acting on psi is the h bar times m times psi, right? And remember that psi, like I said, has a radial comma. Remember that psi of r, theta, and phi was the r of r and then the YLMs. Right, and if we put in the actual quantum numbers, this is YNLM, and so is this, right? Oh, sorry, right. There's no M in the R equation. There is an L. Yes, there is an L. If we remember correctly, at least for the hydrogen atom. So this is as an example for the hydrogen atom. There's N and L. Okay. So if we restrict ourselves to the hydrogen atom, we have an N and L. And then we would write NLM here, right? But in general, this is true. So even if we're not looking at the hydrogen atom, right, this is true. Okay, all right. As long as we're in spherical coordinates, right? So we're in the spherical coordinates, r theta phi. Okay, all right. I think that's it for tonight, and I'll put a homework up, and then don't forget you have a quiz as well starting tomorrow morning, Friday.